Hi, Paul 251 students. We are now going to talk about the standard normal distribution and z-scores. This is the last lecture in the week 11 series. So when I was talking about the central limit theorem, one thing that stood out repeatedly was this normal distribution of the sampling distribution of means. And I kept talking about this being a nice bell curve shaped distribution. I talked about it being symmetrical, where half of the data fall to the left, the other fall to the right, centered upon a mean that is in the middle. So our normal distribution of a sampling distribution, or our standard normal distribution, has the following properties. First, it has a mean, which is at this peak here, of 0. And here this mu, lowercase mu, is the notation for the mean of this standard normal distribution. The second property is that it has a standard deviation of 1. And that is notated here with this lowercase sigma. Knowing these properties, we can use the standard normal distribution to transform observed values in a data set, such as the number of days a week that a student reports reading political news, into z-scores. And what we can do here, we have our x-axis that has these values of z. And these values of z actually will now represent how many standard deviations an observed value is from the mean. So if a student reports that he reads the news 7 days a week, we can figure out using a z-score how many standard deviations that 7 days a week is from the mean of the whole group. Further, using z-scores and this standard normal distribution, we can start calculating probabilities. So just like we were calculating the probability of rolling a 6-sided die and landing on a 1, or flipping a coin and landing on tails, we can now use the standard normal distribution to figure out the probability of observing certain values in a data set. Like figuring out, well, what is the probability that a student is reading the news 7 days a week? So let's talk through how we can do this. So when we have our z-scores, here is the basic formula for doing this. Z here is represented by the calculation of numerator over denominator. In our numerator, we start off with x. This is the value of our observed data point, or our observed raw score. And I believe in the homework, I call these raw scores or data points. So here we have our observed raw score. Subtracted from that, we have the mean of our population, mu. And then in our denominator, we have our standard deviation of the population, sigma. Another way of restating this formula in plain language is that our z-score has a numerator of data point minus the mean and a denominator of standard deviation. In essence, once we do this calculation and figure out our value of z, this is going to represent the number of standard deviations between a raw score and the population mean. Now, keep in mind, I've said this word population a few times. So when I'm talking about using these z-scores, it is assuming that we know something about our actual population of interest. So if I care about the news reading habits of Paul 251 students, to calculate z-scores, I'm going to need to know that population mean and that population standard deviation. If I were simply to say, oh, I have a sample of 30 students, and I just have that sample mean or sample deviation, That's not enough to calculate Z. So as you're going through homework 5, homework 6, and then ultimately the final exam, keep in mind when I give you information about a population or a sample. If we're going to be using the Z-score and the standard normal distribution, I'm going to have to provide you a population mean and a population standard deviation. So let's talk a little bit more about what these Z-scores mean once they're calculated. So here again, I have a graph of my standard normal distribution. Its x-axis are these Z-scores that are calculated with this formula, data point minus mean over standard deviation. A Z-score of 0 means that the observed value or that element is at the mean. And this makes sense. So if we think about if x, our observed value, is equal to mu, these two values will cancel out and we'll have a numerator of 0. So in this case, when x equals mu, when our observed value or that observed element equals the mean, we will have a Z-score of 0. Next, if we have an element greater than the mean, or if we're observing a raw score or data point that's greater than the mean, our x is going to be larger than our mu. So if we subtract mu from x, we're going to have a positive number. This numerator here is going to be positive. So therefore, a positive Z-score is going to represent an element or a raw score greater than the mean. Then finally, if we have an element or a raw score or a data point that is less than the mean, in this case, our x is less than mu. Well, if we're subtracting mu from x and mu is greater, we're going to end up with a negative number in this numerator. So when that happens, our overall Z-score is going to be negative. And therefore, this negative Z-score will represent a raw score that's less than the mean. So a couple rules that now translate Z-scores into probabilities. Based on the standard normal distribution, if we have a large enough number of observations, so if our sample is sufficiently large, as most samples will be, 68% of all of our observations in this infinite sampling will have a Z-score between plus and minus 1. 95% of our observations will have a Z-score between plus and minus 2. And then finally, about 99% of all observed values will have a Z-score that falls between plus and minus 3. Basically, when we look at these Z-scores, it's going to show this relationship between how extreme a value is and how frequently it occurs. So if we have a really extreme value that falls very far from the mean, we're not going to observe it very frequently. A Z-score of, say, positive 3 is going to occur probably less than 1% of the time. So with that, we can start to use Z-scores to find probabilities. So let's walk through this with an exercise. Again, here are our formulas for calculating Z-scores. First with just the symbols, then in plain language. And in our example, we're going to go back and talk about Poll 251 political news consumption. And here, we're going to make some assumptions. I'm going to say that the data that I have from the class is that of the full population of 251 students. And in the previous slides, I said that the mean was 4.94. I'm just going to round that up to 5 for ease of math. So here we're dealing with a population mean mu of 5. 5 days a week is the mean number of days students read the news. We also have a standard deviation value for this population. That is our lowercase sigma, and that is 1.75 days. So with that, we're going to answer the following 4 questions. What is the z-score associated with reading the news 7 days a week? Was the z-score associated with reading the news 2.5 days a week? Was the z-score, what percent observed days fall below 1.5 days a week? And then what percentage of observed days fall between 3.25 and 6.75 days a week? So I did all of this math on the whiteboard in my home office. At the top here, I put our formula for our z-scores. It is our observed raw score value, x. Subtracted from that, we have our mean of mu, which is 5 days. And then our denominator is sigma, which is given to us as 1.75 days. So question 1, what is the z-score associated with reading the news 7 days a week? So here, instead of x, I plug in 7 because that is my observed value of news consumption. From that, I'm subtracting my mu of 5 and then dividing by 1.75. So I do that math. 7 minus 5 is 2, and I divide that by 1.75, and that gives us an answer of 1.14. So our z-score associated with reading the news 7 days a week is 1.14. Next, what is the z-score associated with reading the news 2.5 days a week? Here again, I have that same calculation for z, and I plug in as my value of x, or my observed data point, 2.5. From it, I'm going to subtract 5, which is my mean, and then divide it by my standard deviation of 1.75. So here my numerator, 2.5 minus 5 is negative 2.5. I divide that by 1.75, and I get a z-score of negative 1.43. Okay, so that is the z-score associated with reading the news 2.5 days a week. Next question. What percentage of observed days fall below reading the news 1.5 days a week? So in order to solve this question, the first thing we'll need to do is calculate the z-score associated with reading the news 1.5 days a week. So that's what I'm doing on this line right here. I have my z-score formula. I plug in 1.5 for my value of x. From it, I subtract 5. And then I divide that all by 1.75. So here's my numerator. 1.5 minus 5 is negative 3.5. I divide that by 1.75 and get negative 2. Here now, I'm going to rely upon those rules that I told you about the standard normal distribution. And one thing I told you is that in our standard normal distribution, which I've drawn here on my whiteboard, it has a mean of 0, and 95% of all observed cases fall between plus and minus 2 standard deviations, or they fall between -2 and +2 z-scores. So if I want to know the percentage of observed days that fall below a z-score of 2, well, if what's in the middle here is 95%, our tails are going to cumulatively add up to 5%. So we'll have 2.5% of cases falling below -2 and 2.5% of cases falling above +2. So to answer this question, what percentage of observed days fall below 1.5 days a week? That answer is 2.5%. What we know from the standard normal distribution is 95% of all data fall between plus and -2. So that means 5% doesn't, and half of that 5% falls below -2, and that's 2.5%. Finally, what percentage of observed days fall between 3.25 and 6.75 days a week? To solve this, step 1 is to calculate the z-scores associated with 3.25 and 6.75. I do that here. First, I have my numerator 3.25 minus 5. That is negative 1.75. I divide that by my standard deviation of 1.75 and get negative 1. So the z-score associated with 3.25 is negative 1. I do the same for the 6.75 days a week. So here in my numerator, I have 6.75 minus 5. That is 1.75. Divide that by 1.75 and I get positive 1. So the z-score associated with 6.75 days a week is positive 1. So now I'm asking, what percent of observed days fall in this range? What is the percentage of cases or observed values that fall between plus or minus 1 z-scores? Well, as I was talking about in the rules of the standard normal distribution, what we know is that 68% of all cases fall between plus and minus 1 standard deviation of the mean, or 68% of all cases fall within plus and minus 1 z-score. So there's your answer. Hopefully this helps you out. Another practice exercise will be posted on Blackboard as an assignment that you can complete. Hopefully that will help you out, and hopefully this will help you get homework 5 completed as well. Let me know if you have any questions.